Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amar Abdullah bin Mansur. My matric number is 2313122778. Okay, today we would like to present our project title, which means Design, Improvement and Analysis of Aircraft Engine Bracket, which is part of our Computer Aided Engineering course. In the aerospace industry, it is very important to design components that are lightweight but still strong. One of these components is the aircraft engine bracket, which support the engine cooling during maintenance. Also, it does not directly help the engine to function. It must be able to handle high mechanical load and survive in harsh operating conditions. This bracket is usually made from titanium alloy because of its strength and corrosion resistance. However, titanium is very expensive and consumes a lot of energy to produce. That's why we focus on finding a better design and also exploring alternative materials that are more sustainable and cost effective. Next slide is objective. This project was carried out with the following objective. First objective is to redesign the aircraft engine bracket using computer aided design tool to reduce mass while keeping its structure strength. Second objective is to find and evaluate alternative metallic material to replace titanium alloy, focus on sustainability and lower production energy. Third, to perform linear static analysis to make sure the bracket can hold a 60,500 Newton load, have a mass below 0.8 kg, maintain a factor of safety between 1.2 and 3.0, and show deflection less than 0.35 mm. Next, to conduct thermal stress analysis to study how the bracket behave under temperature change. Next objective is to perform model analysis to find the natural frequencies of the bracket and avoid resonance with engine vibration.
Let me start by explaining the design criteria that must be made for our aircraft engine bracket. First, the material must be metallic to ensure high strength and structural integrity under aerospace conditions. 2. The bracket must be able to withstand a load of 16,500 newtons. This represents the expected operational load during engine use. 3. The mass of the bracket must be less than 0.8 kg while maintaining a factor of safety FOS of at least 1.2. However, we are also constrained to not exceed an FOS of 3.0 to avoid over-design. 4. The maximum deflection allowed is 0.35 mm to ensure the dimensional stability under load. 5. For simulation, we will use a mesh size of 3.0 mm and the total number of mesh elements must not exceed 120,000. This ensures a balance between accuracy and computational efficiency. Now, moving on the dimensional constraint of the bracket, the design must accommodate 4 holes with diameter of 10 mm, which serve a friction point. The distance between holes along the base is 148 mm and 74 mm on the other side, as shown in the drawing. All holes must be positioned at a union height of 23 mm from the bottom. The hole for loading where the 16,500 Newton force is applied must have a diameter of 19 mm and a length of 35 mm. Critical distance such as the 20 mm and 35 mm offset from the load hole ensure precise load placement and force distribution. These dimensions are critical to ensuring compatibility with the overall engine mounting system and must be strictly followed.
So for the design, our group have designed 3 of the engine aircraft bracket. So for the first design, the mass is 0.7726 kg. The deformation is 0.22596 mm and the FOS is 2.3783. So for this design, this is a failure because it does not meet the requirement that have been given. So for the design 2, which is created or designed by ANIC, the mass is 0.76629 kg. The deformation is 0.24203 mm and the FOS 2.54543. So this design is meet the requirement that have been given. So this is our final design. And lastly is the design by me, Muhammad Aris Izhan. So for the mass is 0.59899 kg. The deformation is 0.36542 mm and the FOS 0.82942. That doesn't meet the requirement that have been given.
Let's begin by understanding what linear static structural analysis is. It is a simulation technique used to determine how a component behaves when subjected to constant or steady load. Its mean does not account for dynamic effect or change over time. The main purpose are to evaluate stress, strain and deformation in the part, and to ensure that the component can handle applied load safely without failure. To perform this simulation, we follow a structured setup process. First, the 3D model was created using CATIA, which allowed us to precisely define the geometry of the part. The material selected for the simulation was aluminium alloy 7075T6, which is commonly used in high-strength structural application due to its excellent strength-to-weight ratio. For the meshing process, we use tetrahedral element with a mesh size of 3 mm, which provide a good balance between accuracy and computational efficiency. Next, the boundary condition was set by applying a fixed support at 4 holes, each with a diameter of 10 mm to simulate how the part is mounted or held in place. Finally, a load of 16,500 Newton was applied at the loading hole, which has a diameter of 19 mm. This simulate the real operational force acting on the component during uses. On the right side, the image shows different stages of the setup, including the meshing and how the boundary condition and load were applied. Now, let's look at the result from the simulation. The total deformation record was 0.24203 mm, which show the maximum displacement of the part under the applied load. This indicates that the component maintains its shape well and does not experience excessive bending or movement. The equivalent stress, also known as von Mises stress, was 204.94 MPa. This value tells us how close the material is to yielding under the combined loading condition. Finally, the factor of safety, or FOS, was 2.4543. This means the component can withstand about 2.45 times the applied load before failure, which is a safe and acceptable range for structural application. This result confirms that the design is both strong and reliable under the given condition.
Now, let's move on to the thermal stress analysis section. Thermal stress analysis is a type of structural analysis that is used to study how a component behaves when it is exposed to temperature change. This type of analysis takes into account the effect of thermal expansion or construction, especially when the part is constrained and cannot freely expand or shrink. This is very important in aerospace application because temperature can change significantly during flight or engine operation, which may lead to deformation, crack, or even failure if not properly designed. The purpose of doing this analysis is first to determine how thermal stress is distributed through the bracket when it experiences temperature variation. Second, to identify high stress region that might cause deformation or failure over time. And last one is to ensure that the bracket can perform well under both mechanical and thermal load. Next is experimental setup and procedure. For this simulation, we follow the setup below. First, geometry and material assignment. From this step, we create a duplicate of the linear static analysis file in ANSYS. Then, we went into the engineering data section and drag the isotropic instantaneous coefficient under aluminum alloy. This was done to define the material thermal properties, specifically to input value related to temperature. Next step is steady state thermal analysis. We open the thermal model. Once inside, we navigate to the static structure section. Then select load and choose thermal condition. In this section, we set the operating temperature to 30 Celsius, which is the temperature we use for this analysis. After that, we return to the static structure setup and set the ambient or initial temperature to 22 Celsius to simulate environmental condition. Next, static structure with thermal load. In this step, no major change since we had already duplicated the previous setup. The feed support and apply load remain in the same position and with the same value as in the original linear static setup. Once everything was complete, we run the simulation to obtain the final result. Result of thermal stress analysis without thermal load. First, deformation result is 0.24203 mm. Next, stress result is 204.94 MPa. And FOS result is 2.4543. With thermal load, for deformation result is 0.24247 mm. Stress result is 221.55 MPa. And last, for FOS result is 2.2704.
So for the free vibration analysis, the definition of the free vibration analysis is a type of dynamic analysis that studies how to structure or component vibrate naturally when it is distracted and then allowed to vibrate on its own without any continuous external force. It is focused on determining the system natural frequencies, resonant frequencies, mode shape, the structure assumed at the natural frequency. So for the purpose of the free vibration analysis, to identify the natural frequencies at which a structures tend to vibrate. To avoid resonance, which occurred the excitation frequency match a natural frequency, potentially causing catastrophic failure. So for the experimental setup and procedures, the geometry and model preparation, the CAD model we use CATIA to redesign aircraft engine bracket to ensure the accurate geometry for model analysis. So for the material assignment, we use aluminum alloy 7075 T6 due to its lightweight characteristic and potential for sustainable use. It is aligned to SDG 12 goals. So for the model setup in model analysis system, the model was imported to ANSYS workbench where a model analysis system was created to identify the natural frequencies and corresponding mode shapes. So for the model meshing the model, a size of 3 mm was used to ensure the mesh quality remains within the constraint of less than 120,000 element, providing a balance between accuracy and computation efficiency. So for the boundary condition which is support, feed support will apply at the mounting holes to simulate the actual constraints condition experienced by the bracket during operation. So the defined number of modes, the analysis was set to extract the first 5 natural modes, which are sufficient to detect any potential resonance within the operational frequency range. So for the solving the model, the simulation was then solved to determine the bracket natural frequencies and mode shapes under free vibration condition. So for the result of free vibration analysis, we have 4, which is natural frequency table. The first 5 natural frequencies of the bracket were found to be 145.6 Hz, 260.3 Hz, 390.8 Hz, 512.7 Hz, and 645.2 Hz respectively. So second, the mode shape visualization Each mode shape illustrates how the bracket vibrates at a particular frequency. Height deformation area are indicated in the red while minimal movement is shown in blue. So for the interpretation of result, since none of the identified natural frequency fall within the typical engine excitation range, which is 5 to 100 Hz, the risk of resonance is considered minimal. So for the conclusion and sustainability link, the result confirmed that the redesigned bracket not only avoid resonance but also maintain structural integrity with a reduced mass, promoting material efficiency and supporting responsible consumption in line with SDG 12. Thank you.